Good morning. Um, this is the Bayesian machine learning class, and so today we're going to talk about classification. Um, as you have seen, there are two approaches to classification. Right? There's a generative approach and there's a discriminative approach. And in the generative approach, I hope you've recognized that there are a lot of similarities between that approach and density estimation and fitting a Gaussian. What we did there is we just built what's called a generative model. That means we build a model for all the variables in the system, a joint. And so the variables are X inputs, features as they're called in classification, and outputs Y or classes. So we build a model P of X comma Y, a joint distribution of X and Y. Once we have a joint distribution, well, you can basically answer any question that you have by conditioning, right? Or by using probability theory. And the question that we have to the model will be, what's the posterior distribution for classes given inputs, right? We want to compute P of Y given X. And the way we play the game then is we actually build a model for what we call a priori assignment of classes. Basically, we say, well, let's just, if I haven't seen any training data, we have a categorical distribution over classes. And we say, well, class conditional data distribution. Given a class, I assume that the data, the features have a Gaussian distribution. And with that, those assumptions, everything is just analytically solvable. And that's what we do in this class. The only thing really we do is we make a choice to build a generative model. We make a choice for a prior over classes categorical distribution and a choice that the data or the features for a class are Gaussian distributed. Those are the only assumptions, and the rest follows straight from probability theory. Now, the nice thing, of course, is that if you make these assumptions, a categorical prior distribution and a Gaussian distribution for the features, that everything is analytically solvable. So you will get you will get analytical formulas for the maximum likelihood estimates of the parameters. You can also do it in a Bayesian way, by the way, but here we chose to do it in a maximum likelihood, and you get also the prediction for a class given a new input gives you an analytical formula or closed form formula. So executing and training a classifier with this approach is almost instantaneous on your computer. You can have a large database of examples, but if you program this in Python or MATLAB and it's just a few equations, you have and you press execute, it trains in a second, and in a millisecond you have your prediction because everything is closed form. So it's a really, really nice approach. As long as your assumptions are reasonable, right? As long as your data is indeed, let's say, the features for a given class are at least distributed as a Gaussian. If that's not the case, if you cannot make these assumptions, right? You can, for instance, plot your data set and you see, and you look at it and you say, nah, that doesn't look like Gaussian at all. I'm not going to do that. Then there's another approach called discriminative classification. So I'm not concerned now about what is the distribution of the features. I'm just going to build a model for that discrimination boundary between the classes. And that approach looks a lot like regression. You will see in that class, the discriminative classification class, that later on when we do maximum likelihood, you'll see update formulas based on the gradient that basically look exact, or not exactly, of course, but that basically look like the same formulas as we did for regression. So you can do so. What the idea here is we just assume here immediately that we're going to model the probability distribution for the classes given the inputs immediately. So we're not going to do a joint over X and Y. We're just going to model the conditional distribution for the classes given X. There's no Bayes rule involved. Just build that model. If we assume that that the model, let's say, looks the same as the outcome that we had for a generative classification, namely we want a line, and if we want to put that in probabilistic terms, that means you're going to have the a normalized exponential of that line. That's just how probabilities work. But another way of doing that is just look at the outcome for probabilistic for generative classification. You found there a softmax function of a line. And in discriminative classification, you can say, okay, I'm just going to look for a softmax function of a line. And you can do Bayesian discriminative classification by setting a prior on the weights. And then you can just write down your formulas. Everything is fine. The issue then is that if you can write down your posterior for your weights, and you can write down your predicted class given inputs. You see these integrals, but you don't get really, you can work them out analytically, right? So that's a problem. And then, you know, we descend in this class into one of the approximation methods that is very common in the Bayesian literature. And one of those methods is called Laplace approximation. Basically, you say, well, if I have some kind of a distribution, I don't know what it looks like, I'm just going to try to approximate it by a Gaussian. And once I have a Gaussian, then I can solve it. By itself, Laplace approximation has nothing to do with Bayesian estimation. It's just a procedure for approximating a distribution or a function by a Gaussian. That's all it is. It just happens to be useful in Bayesian machine learning, because if we can approximate a distribution by a Gaussian, then very often we can solve the integral or whatever it is that we want to compute with a Gaussian. So that's what we do in this class. And that turns out that if we do that, in one way, it's completely straightforward. It's just following a simple recipe. In the other way, if you work it out numerically, the formulas get so complex that I would never ask you to reproduce that kind of complexity in an exam. I just want to show that it's possible to do it, and you get good answers. And somebody solved it for us in a paper, and that paper was published. And then since then, everybody can solve Bayesian logistic regression or Bayesian discriminative classification using the Laplace method, because some researcher worked it out for us. So that's also a great method, particularly when you cannot make the strong Gaussian assumptions. Yeah, you have two methods now. If you think the assumptions are correct for the Gaussian assumptions for the features, then I recommend using the generative classification approach. If you feel that's not a correct way, then I think you have to go to discriminative classification. Yeah, that's more work. The equations are, they look nasty, but I mean, people have worked it out for you, so it's still quite easy to program, and you will get good results too. So those are two approaches. One that looks a lot like density estimation, the other looks a lot like regression. Yeah, these are basically the two main approaches in classification. I'm going to leave it now to you to ask questions about this class. Gautam, go ahead.
Hello, Professor Bert. I had a question in the ML estimation part for the discriminative classification section. So,
Yeah.
yeah, so in that section, near to the end where we talk about the updation of the parameters, we have a line which says that in the Bayesian approach, we get to update theta with precision weighted prediction errors, while in the maximal likelihood approach, we just weighted based on the input values. So that was a bit confusing for me. I didn't clearly understand the interpretation of that. Is that something which is related to the whole Kalman gain thing that we studied in the sequential Bayesian updation? Yeah, but if you could just explain that a bit more, that would be great.
Yes, I will do that. Let me just share my screen.
Yeah.
It's quite a general remark and I didn't mean to confuse you with it, but it's a general remark that here we're treating maximum likelihood estimation for the parameters in a discriminative classification. So you just build your likelihood and you say, well, I'm going to just take here the derivative or the gradient, and then I'm just going to do gradient descent, right? Something like that. And you see that gradient, oh, we recognize again uh, the target from the data set, right? This is given. I mean, you observe for in the data set y and k, it's either 1 or 0. And this here is a term that is the prediction by your model, right? I mean, your model, you're going to plug in some parameter values and you get your input and then you get some prediction. So you have your what we call prediction error. And apparently the gradient, yeah, or the prediction error is multiplied by xn. And in one way, I mean, the whole point of learning is to get rid of prediction errors, right? If the prediction error is 0, well, then you're done learning. So it makes sense that the gradient is going to be a function of the something times a prediction error. Now, if we compare this to what we did in another class, and maybe it's yeah, it's the really the proper the, unfortunately it doesn't, well, maybe it starts to render later. The proper comparison would be, of course, to do a Bayesian approach to the discriminative classification. But what I wanted to show is that if we here we have this, I think we are observing Gaussians and we do a Kalman filter kind of thing. And what you see is, okay, I also update my weights here, the mean with, yeah, here's a prediction error. This is my new observation. This was the previous mean, which I can use as a prediction for, let's say for the prediction for U of t. And then there's a Kalman gain. And that Kalman gain that has, yeah, that's a ratio of variances or ratio of prediction of precisions. So what happens? And so what happens is that in the Bayesian way, you can see this as gradient-based adaptation, and the learning rate, the Kalman gain, is basically is computed by the Bayesian procedure. Right? You have an adaptive learning rate here, K. Kalman gain is, if you will, the learning rate, because you say mu1 is mu0 plus some learning rate times the prediction error. And also here, mu t is the previous value plus some learning rate times the prediction error. And this prediction error, this learning rate, I don't have to just set a value. that I choose. Normally in a procedure like LMS, you have to set a value, a step size. No, it's computed. In the Bayesian approach, your learning rate, your step size is pre-computed. You don't get that benefit if you do maximum likelihood estimation and you compute a gradient. I'm going back now all the way to the bottom again. Fortunately, because I'm also running Teams, it just renders really slow, but it will get there. So if you do regression, or let's say maximum likelihood estimation, and you say I'm gonna try to find the parameters by gradient descent on the likelihood, you'll do something like this. You say, okay, here I have a nice, I have my gradient. There's a prediction error, and my update for my parameter is my previous value times some learning rate times, yeah, the input times a prediction. In the Bayesian approach, this learning rate times input would be computed online. I mean, it's part of the uncertainties, right? And here you just have to choose, but there's no tuning parameter. Here you have to choose a tuning parameter. And that's really what I wanted to say. And that makes this a lot harder to do, because how do you set the tuning parameter, right? 0.01 or 0.0001. So you have no tuning parameters in a Bayesian approach. You get similar formulas for adaptation, but this tuning parameter, the step size, disappears in a Bayesian approach. It's pre-computed. It's called a Kalman gain. That was my point. And we can do it because in a Bayesian approach, we have estimates of, of precisions, of variances. And those estimates give me basically an insight in how much do I want to learn and how much do I want to forget. It's a bit of a roundabout way of explaining it, in too many words, but I hope you sort of get the point.
Yes, I understand. Yeah. Sorry. So I understand the concept that you mentioned, but the one thing that I'm still doubtful about is the fact that we say if we use the Bayesian approach, it's going to be more precise than the ML approach. So like, as you said, in the Bayesian, there'll be a pre-computed learning rate in a sense, right? So, but here we get to update the values of like the eta or the learning rate to our adjustments, right? So we can fine tune it and we can make it either 0.00101 or something, and hence we have a say in how precise the gradient goes down, right? Or is that a wrong interpretation?
No. I mean, the first thing is, of course, that in the maximum likelihood approach to classification, right? You update these parameters, and you don't have any uncertainty about these parameters. You just, we're doing maximum likelihood. We just update, what you say, the parameters. So let's. The Bayesian approach, that would be assuming a delta distribution over the parameters, right? But the way we do it, why don't we have, like in the Bayesian approach, the Kalman filter, you will see no tuning parameters. There's no parameter that you have to set. You make your assumptions about your model, and then after that, it's all basically probability theory. There's no extra parameters you have to put in. Now, if you do maximum likelihood estimation and you cannot find an analytical solution, but you have to do it by gradient descent, like we do here, then you have to choose here eta, your tuning parameter. Now, I'm sure that, so there is a whole literature on how to adapt step sizes with gradient descent, right? You start small and then you make it even smaller, and if sometimes you make it larger. There's a lot of literature over that. So you will get an answer. It's just in some way there is something missing here, namely by the Bayesian approach actually gives the proper value for this eta, if you will, right? We compute some uncertainty for theta, but that uncertainty helps us construct a proper learning rate. And so there are no tuning parameters. The Bayesian approach is the precise way of updating, if you will.
Yep.
There's nothing left to approximation anymore. I mean, unless you start to approximate the Bayesian approach, right? But there is no. Once you build your models, your equations may look like this, your update equations in the Bayesian approach, but there's not going to be a parameter eta that you have to just set and come up with. No ad hocery in the Bayesian approach. That's the only point I wanted to make. By choosing maximum likelihood, gradient descent, and now you have a tuning parameter to fix, and you have then you have to go to the literature and or you choose it really small and you and you just hope you don't overshoot or it converges. You don't have any of these problems in the Bayesian approach. So if at all possible, choose a Bayesian approach. The only problem is that it may be numerically hard to solve, right? Maybe analytically hard to solve, and you have to, then you have to go to numerical recipes. But I think that's you want to start out with formulating a problem in a Bayesian way, and then consider, okay, now we need to execute this. How I'm going to execute it, right? Every time when you don't do a Bayesian approach, you generally wind up with stuff like this where you have to choose tuning parameters. There are no tuning parameters in the Bayesian approach.
Yeah, got it. Yep.
Yep. Okay. Okay.
Yep.
It's a bit of I totally agree that it's a bit of a side remark that and the examples aren't optimally chosen, but it's generally true that you don't have tuning parameters if you do machine learning in a proper Bayesian way. And once you start to make approximations like maximum likelihood, then all these tuning parameters appear, like step sizes, learning rates, stopping criteria, all that stuff, right? They're just validation sets and test sets of data. Yeah, that's also an arbitrary thing. Yeah, if you have to split your data set in a test set and a training set or a validation set, that means your results are going to depend on how you split that up. If you would select another batch of examples as your training set, you do another split, you get a different result. And also your let's say the error on the test set will be different. So ad hocery creeps in the more you deviate from the Bayesian approach. If you choose a Bayesian approach, you state your assumptions up front. This is my model. After that, it's automated, right? It's just probability theory. There's no more. And if you can execute that probability theory, then it's done. There's no ad hocery. Sorry for the long answer, but any other question? Sveta?
Hi. So in the discriminative classification, we specified the model for the posterior distribution, and we choose it to be a softmax function. But in the generative classification, we could arrive that the posterior will indeed be softmax because of the prior and how the prior is chosen and how the likelihood turns out to be. So isn't so what I'm not able to grasp is shouldn't in the discriminative classification also, shouldn't it come as a result that the posterior is indeed softmax?
Okay, so let's see. So this is the discriminative, and I want. So I'm going to open. I want to also open. Just duplicate this, and then I'm going to open. Actually, I'm going to go to the generative classification because I want to show the comparison. Here, generative classification. Sorry that it takes so long. I have a really old MacBook. Okay, so in generative classification, you make two assumptions, right? You make here your an assumption for the likelihood, and you make an assumption for the prior. Right here, this is your model assumption for likelihood. This is some Gaussian, and here for the prior for the classes. After that, everything is just probability theory, right? We do parameter inference, blah, 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 and we do the class prediction. We just compute here the posterior for the class. We just execute, we marginalize out everything that we know about the parameters, blah, blah, blah. And it just turns out that, okay, the outcome happens to be some function of a linear function of the input. And that function, that is called a normalized exponential function or softmax function. It's basically, it turns this into a proper probability distribution. No matter what beta k x plus gamma is, right? If I sum over the classes, if I sum over the classes k or ck, these probabilities always add up to 1 by construction. So this is a way of turning some line into, this is just a line over for x, right? Some line over into a probability distribution that is always normalized. Why is it called softmax? Well, basically, let's say you wouldn't have the sigma, right? If we just say that P of CK would be beta K gamma, which class would you choose? Well, you would choose the one that for which that this argument is maximum. The softmax function doesn't change the order. Let's say if beta K if beta k x plus gamma is maximum for k equals 2, then it will still be maximum for k equals 2 once after I take the softmax. So it maintains the max, but everything becomes a little softer because now all these values have to add up to 1. That's what the softmax function does. And it rolls out, right? I didn't make the assumption, it just rolls out. And now we go to discriminative classification and it looks like this, right? And the distribution of the features for the red class, well, that's not I mean, that doesn't look like a Gaussian, right? So we can't make that assumption. Basically, the proper way, I mean, there's two ways to go about this now, right? I say, okay, I want to build a model for this. I want to build straight a model for assigning y to a class given the input. And you can go two ways. You can say, oh, let me be inspired by what happened in the generative approach. Namely, I had some softmax function of a linear function of x. I could have said here plus gamma, right? Or I could have called this beta times xn plus gamma. But generally we just add a 1 to the features xn, and then that gamma is incorporated. So this is just shorthand, but it comes down to the same thing. So one way is just to say, oh, we just assume this because this turned out to be that the discrimination functions are a line, and now the only problem is let's come up with the w's, right? The other way is that we say, oh, I want this to be true. Because then my discrimination boundaries, no, this is this is not the right way to go about it. So probably this is the best way to argue about it, is to just say, yeah, I want the discrimination boundaries to be lines. So the posterior probability is just some, I want to compute some line of xn, and I want to choose what is the maximum, but it has to be a probability, right? They have to, if I sum over all classes k, again, it has to sum to 1. So I need to take a softmax function. And that's what we do here. So we just copy basically what the result was for generative classification. We just copy that for here. So now this is the model assumption, if you will. This is the model assumption for discriminative classification. This is the, if you will, the likelihood function for W, and then we choose a prior for W later here. Here, a prior for W. So I don't think it is correct to say that for discriminative classification, that the softmax also is some emerging property. It's really something we choose up front. We choose this as the likelihood function for W, and we choose this here as the prior for W. Right, and you will see that here. Just a different model definition. Is that clear?
Kind of. So my question is, okay, like, why would I intuitively want to choose a softmax function? It's because you still want the summation of all the probabilities to add up to 1, and is that the
well okay? So I mean, as you've seen from the generative approach, right? The discriminate. I mean, we just choose here. I mean, it's a choice, right? We could choose anything, really, anything that you want, but you have to make sure that if you sum over all classes, if you, I mean, there are only 2 classes here, yn equals 0 or 1, right? So once I choose here pyn equals 1, then the probability for yn equals 0 is just 1 minus this, right? So, but you could use any probability distribution as long as it sums to 1. It's up to you to choose. But by choosing this function, we know that the discrimination boundaries are lines, right? I mean, I can verify that by doing this. I can compute the discrimination boundaries by solving this equation, and you'll see, oh, that's just a line. And the other thing is the normalization thing, and then the normalized exponential is just a convenient function. We could have chosen another function that makes that makes sure that no matter what you do, you always have a normalized function for this probability distribution. So you don't have to choose the softmax function, but it's a logical choice. It's a good choice. It works for the generative classification method, and you should see it in the context of discriminative classification as a choice. You could have made another choice, but here it is a choice. In the generative classification method, it was an emerging property, because if you, yeah, that's probably how I want to phrase it. Yeah. So you're not obliged to choose this, but if you choose this, you know your discrimination boundary is going to be a line. And if you wanted to choose W1 times, let's say, xn squared plus W0 times x, then you know your discrimination boundary is going to be a parabola. And you can still take the sigma of that. That just turns that into a normalized function, a normalized and positive function.
Right. Okay. Could you
Right.
explain the discrimination boundaries once more?
Yeah. So the discrimination boundaries between classes, let's say, the line, basically in this feature space, discrimination boundaries are the curves where the probability for the blue class and the probability for the red class are both half. And the way I compute that is, I say, well, the probability that yn is, let's say, belongs to class K, or let's say the blue class, divided by the probability that yn belongs to the red class, given the same input, must be 1. If I solve this equation, then I get the discrimination boundary. Then I get the curve where the probability for the red class is half and the probability for the blue class is half. So this is what you want to solve. So if you plug in this here for yn, so what you'll get is this probability for class 1, and you know that the probability for yn equals 0 is going to be 1 minus this. So what you'll get is sigma of wx divided by sigma of, divided by 1 minus sigma of wx. And that must be 1. And you want to solve that. And it's a good exercise. Try to solve it and you'll see that a line comes out. And what you can use is this property. So if you can solve this equation, so this equation, right, for class yn, let's say red and blue, and that means for yn equals 1 divided by pyn equals 0, and you want to solve that for this, then I hope you can find that it will be a good exercise for the exam. You should be able to find that the discrimination boundary is a line in feature space.
Yeah. All right. And if I may ask, what's the exclamatory mark indicate?
Oh, yeah, that just means that. Okay, that just means we have to set this. I mean, generally, it's not the case that this probability ratio happens to be 1. It's not always 1, but it just means we for this condition we set it to be 1, and then we right, and then we can just evaluate that. You can just, I mean, you can forget about that.
Yeah. Okay.
At the boundary.
At the boundary, yeah.
Thanks.
Okay, good. Any other questions? I still see a hand from Gautam. Is that an old?
Yeah. That
Okay.
was the old one. Yeah. So.
All right. Yeah, Xiao Kai.
Yeah, can you hear me?
Yes.
Yeah, I would like to ask about the questions of softmax function. As I know, it's a normalization function, right? But I
Yeah,
would like to
yeah.
know what is the difference between like choosing the softmax functions and other normalization functions.
Well, okay, what you want is you want a function such that no matter what wxn, what the value is, even if wxn is negative, that this value after, I mean, after you take the function, it should be non-negative, right? Probabilities cannot be negative. And the second thing is that if you sum the probabilities over all classes, then it should add up to 1. So with those two properties, you can choose, from my viewpoint, anything, any function. It's just that the softmax has as a nice property that if for class, let's say that, let's say if wxn for class 1 is greater than wxn for class 2, then that order is preserved, right? It's a this is for the two class. See, whatever the input is, whatever w times xn is, it could be anything on the real line. The output is always sigma of wxn is greater than 1, and it will and it also, I mean, it's bounded, right? It's going to normalize to 1. You don't have to choose this one, right? I mean, you can choose another one. There is another one here, the scaled probit function here, but the probit function is not a function, that's a different function. And that turns out to be very close, right? So there are other functions that you can also choose. You don't have the logistic function or the softmax. It just turns out that because the properties of this function, the normalized exponential, it has a couple of really nice numerical properties, right? Such as this one, and there's an e in here, and that means that you also have that in a Gaussian. So that means that if you work with Gaussians, this generally it gives nice numerical properties. So yeah, and it also happens to be the function that sort of emerges, right, from really basic model assumptions, as we saw in the generative classification class. If we take Gaussian distributed features and categorical distributed classes, then and we try to make a prediction based on that, well, this function, this softmax function, sort of emerges. So it's you can choose any function that you want, but it is a good function for that you see a lot in machine learning, either as an emerging property based on basic assumptions, or people just choose it like this, like I do here. I need a function that turns any argument into a positive or a non-negative value, and it also needs to be a normalized function, right? And yeah, it's in a way there are probably an infinite number of alternative functions, but this one works in practice. But you can choose other functions. Is
Okay,
that
I got it.
yeah?
Yeah, thanks.
Okay. Any other questions? All right. then I think we can close the session. Yeah, I see another question, Sveta.
Yeah, I felt that the material for this class was a bit intense. So I would like to know if we can still ask questions next class as well, after we probably discuss the questions for the material of that class.
Yeah, that's fine. That's fine with me. I mean, I think I agree. This is actually a double class, right? I mean, we do both discriminative and generative classification, and we could have. I mean, either one could just be one class, and it actually was that case in earlier versions. But yeah, it wouldn't fit in the so it's a scheduling issue. But I agree, this is a lot of material. I hope that you you don't. I mean, that you kind of see the forest through the trees, right? That that you don't get too bogged down by working out the Laplace approximation and these Hessians and whatever. That's not something that I expect you to, let's say, to reproduce, particularly not if it's if you know, if it's just, if it turns out that you need to use computational tricks. Working it out for Bayesian logistic regression has been done. I mean, this derivation has been done, but this comes from a paper, right? I mean, somebody derived it, was able to derive it, and wrote a paper about it. So I don't expect you to basically derive a paper in your exam. So I feel I need to put it in the class and work it all the way out in the class so you can see that, yeah, for the probability for the classes given X, there is an analytical solution. It's an approximation, but you do get a nice solution. But and the same thing for deriving this this gradient here. Yeah, I do it in an optional slide, but I mean, it's a gradient. Let's here it is, right? I mean, this is not the kind of derivations that you can do at your exam, right? So in the exam, it's going to be more about that you understand what is the difference between discriminative and generative classification, that you really understand how to set up a model, and if these models are set up with categorical and Gaussians, and you know, you get that you can write down the formulas, and if I give you the formula for multiplication of Gaussians, that you can actually work it out, right? But not so much beyond that, right? I have no intention at all to trick you in the exam, or to make you come up with clever numerical tricks, right? It's already hard enough to do this class completely online. I'm very aware of it. That makes it a lot harder for you. And from my side, then I will try to make the exam pretty straightforward, but I will test you on if you understand the main ideas in this class, the main idea of generative classification, what is really assumed and what follows from it, and also here in discriminative classification, what is assumed here, the argument. The argument for discriminative classification is not as smooth as for the generative classification, right? Because we didn't. I mean, the argument for using sigma was not as smooth as we did for generative classification. But still, when you kind of follow this argument, and you should be able to at least get to this point, right? Where you can, okay, we made a choice for the likelihood function for W, we made a choice for the prior, I get a posterior. This is not a Gaussian. And you should know that there is a Laplace procedure, Laplace approximation. And if everything would be simple, then you should be able to work that out, but not for Bayesian logistic regression, because it turns into pretty much a nightmare with a very nice ending, by the way. Discriminative classification feels a bit more ad hoc, and you are right about that. It is a bit more ad hoc. It's an optional paper. You don't need to really read that paper, but there's a one-page paper, and I'm just, hopefully it's gonna render now. There's a one-page paper that Thomas Minka from currently works at Microsoft, and he says, well, there are these two approaches, generative classification and discriminative classification. Actually, there's only one really proper way of doing it, and that is generative classification. And discriminative classification can be rephrased as generative classification with a different model assumptions. And so, I mean, but the paper is, yeah, is a bit advanced. It's just one page. If you're really into this stuff, you can read it, and you'll see that indeed what we do here in this discriminative classification can be rephrased as generative classification, but you know, you don't need that for the exam. For now, I think it's good enough if you see how discriminative classification really borrows the idea from regression that we're going to model directly a conditional P of y given x. We're going to just build a model for that. And that logistic regression, which is by far the most popular way of doing discriminative classification, borrows a second idea from basically the outcome of generative classification, namely the likelihood function for my weights is going to be this one here. It's just going to be a softmax of some polynomial over x, and the simplest, if you want to have linear discrimination boundaries, is to choose a line, and you can make this a parabola, whatever. But that's the idea of discriminative classification, right? So you just borrow some ideas from. It has something of regression, and it has a little bit of well, it borrows an idea of using this softmax function. But I totally agree. You could have chosen something else, as long as it's a function that transfers whatever the argument is to a non-negative value, and the function also has to imply that it's well, that probabilities are always normalized. Yeah, so that's what I wanted to say about this class. So don't get too, let's say, lost in the details of working out the equations. It's more it's going to be more about insight. Okay. But aside from that, you are always welcome to ask any question on Piazza. Also, you're always welcome to. I mean, we can also have more sessions on looking back on classes. I just think that if I'm going to post, let's say, this class in the little in my table, right, and it says, okay, this is about this is the live class for classification. It should be the live class for classification, and we shouldn't spend half an hour on something else. But outside that recording, we can do, of course, anything. We can discuss anything.
Thanks. Thanks a lot.
Okay. Okay. Cool. All right then. Again, it's been about an hour, so it always takes longer than I think, probably because I talk too much. So are there any other questions? Otherwise, I'm going to stop the recording. Yeah, I'll stop the recording now.